I was just trying to remember, this I think is it might be my 24th visit to Taiwan. Yeah, I've been here a while. But it's actually great to be back, and I'm especially excited if I have a clicker. Yeah, there we go. And I'm especially excited to be here to talk about this topic, which, as you know, is near and dear to my heart, because not only today am I talking about Lunar Lake's GPU, but we're introducing our Xe2 architecture. So Xe2 is our second generation architecture, and as you'll note in this picture, it's a unified architecture. It's going to be servicing multiple markets. On the left here, you'll note our nice brand new Lunar Lake architecture, which is being delivered, with the GPU based on the Xe2 architecture. But on this side, and I'm so excited to say it, is BattleMage, which is our discrete GPU family, which will continue with our Xe2 architecture. So I think this is actually the first time, and it may be the first time I've ever put a slide up with a BattleMage die shot. And what I'm confirming to you today is that Xe2 architecture is going to be used in both devices. Yes, thank you very much. So to start with, let's talk a little bit about what is Xe2. Well, to begin with, it's an evolution, right? We started with Xe. It was our first time doing a discrete GPU family. And we have uncovered, as many of you in the audience know, a lot of stuff. I mean, it's been a journey. And we've learned a lot about CPU limitations, about shader compiling, about DX9. And all of that effort has gone forward into Xe2. So Xe2 is an evolution of Xe that brings higher utilization. So the large investment in silicon that we did in Xe is now being more efficiently utilized. We've improved work distribution, and it is way more software compatible. So think about Xe2 as the next generation of GPU architecture designed to be more compatible with games and to have higher utilization. All right, this is just one way to think about it. I'm not going to release performance today, but this is a set of micro benchmarks. I did a video a while ago about micro benchmarks on Xe, and this is the way that our engineering team evaluates performance, right? It says, I want to look at a specific operation. These big bars, by the way, are our standout improvement on Xe2, where we've actually implemented an instruction called execute indirect in hardware. Execute indirect is used very commonly by game engines to accelerate long command lists, and we had to do that in software emulation, which basically put a lot of pressure on our register file. It had a lot of software unrolling. In this case, we improved performance by 12.5x if you have execute indirects. But the improvements are across the board. It's just a lot of hard engineering work across many years, everybody polishing that thing. You know how engineers are. You get them in a corner, and they just start polishing, right? And these guys have been polishing and polishing and polishing, and that's what Xe2 is all about. The architecture is scalable, which means it's a modular design, so it's built around the Xe core. This is our second generation Xe core, which is built into a render slice. So our kind of building block is Xe core, then into a render slice, and then into the entire implementation. So I'm going to dive into each of these blocks in some detail to give you a sense of what's changed in the architecture. Later on, I'll talk about Lunar Lake, and specifically the implementation. So this is important to get right from the get-go, right? Right now, I'm going to talk about architecture. It's not process, it's not frequencies. It's like all the things that we've done to make the fundamental design of the GPU better. And then later, I'll talk about how is this implemented in Lunar Lake. All right. So the first and most fundamental building block is our second generation Xe core. So the Xe core is our computational block. And you can think about it as the place where all the magic happens. It's where the vector arithmetic happens. It's where our matrix operations happen. And the big news is that it's been completely re-architected and reorganized to be SIMD16. Our prior generation was SIMD8, which means basically there's 8 lanes of computation for every instruction. We've moved that architecture to be 16 wide, which has a lot of efficiency benefits, but also compatibility benefits. So more and more often you'll see games running right out of the box. We do support 8 by 512 vector operations. So we've got 8 copies of XVEs. Each are 16 lanes by 8. We also support XMX engines, which are 8 by 2048. So think about this thing as a monster computation block that has been optimized and improved over the last 3 years. We also have a 192 kilobyte shared L1. All right, so diving into the vector engine, the first thing you'll see is, again, it used to be, this is the old one on the top, that's XE, and on the bottom is XE2. So you'll see down here, if you're able to like count that, it's 16. Okay, that's representing the number of lanes of computation. And going this way, you know, it's basically taking what used to be 2 by 8s, and now it's by 16 for more efficient operation. We also support the XMX matrix operations with lots of different data types. Can anybody tell me, why do we have int2, int4, int8, FP16, and BF16? Anybody? AI. AI, have you heard about it? It's pretty cool. I hear it's going to be big someday. Anyway, supporting all these different matrix types, all those different data types, allows us to get very high tops. And I think we quoted 67 tops, I think. Is that right, Damian? 67 tops. And that's all based on int8. So if you think about it, that's the common quantized size for a matrix operation for AI. Of course, you can get higher if you have smaller data types. We do support extended math, so sine, cosine, log, exponentials. Those are all in that EM stripe there. And lastly, we support three-way co-issue. That means that we can issue both an integer, a floating point, and a transcendental in the same clock. Pretty cool stuff, and it is much more efficient than our prior generation XE. All right, so the XMX is the heart of our AI accelerator, and I'm showing you a little animation. This is showing you 16 by 4 by 4 by 2, which is kind of saying I've got 16 lanes. I can do 4 chunks of 8-bit integer, and I can do 4 at a time because we're 4 deep, and there's 2 operations per MAC. So that's telling you, hey, I've got a lot of goddamn MAC operations, okay? And it's going to run 2048 ops per clock at FP16 and 4096 at int8. Okay, this is, again, the engine that allows us to do really cool AI on our GPU. But it's not just that. We've got lots of different configurations. You can do FP32, FP16, DP4A, int8, BF16, which is increased precision at loss of sort of range, and then int8, and of course int2 and int4. So the numbers get really big for XMX. If we dive into the sort of the bigger slice, we're talking about the render slice. And think about lots of XE cores here. That's the computational engine. But it's surrounded by a lot of logic that is targeted at graphics. We call it our fixed function units. And in there, you'll see lots of changes. Because at the end of the day, XE was a very big step forward for Intel architecture. We unleashed our graphics engine and discovered lots of different bottlenecks that we never saw before. So this architecture is correcting most of that. It's optimized to reduce latency, it removes stalls, and it has dramatically simplified the hardware-software interface. So we're very excited. Okay, so one of the big things we've done up top in the command front end is to implement execute indirect, as I mentioned, directly in hardware. That makes a big difference, and it's used by engines like Unreal 5 extensively. So having support for this in hardware is pretty much a need for next generation games. On the geometry block, we've improved fetch, and we also have done a much better job with shading. We've redone how work is distributed to the geometry pipeline to improve utilization by a ton. And mesh shading performance has increased dramatically with vertex reuse. We now support what's called a stripe. If you think about DirectX, a lot of the time you have a vertex that's used across multiple triangles. We now take advantage of that in hardware and avoid a second fetch. Okay, if you dive into the next block, we've got out-of-order sampling in XE2 with compressed textures. That is a very, very important technique. So as you know, games have these gigantic multi-gigabyte textures that are mapping trees and forests and hills and stuff. So we compress those, and they go into our cache compressed. So we need to be able to sample out of order, and that's a new feature for XE2. We support 2x the throughput on a sampler read, and we support programmable offsets. All this a little bit technical, but if you think about a programmable offset, we're talking about an offset relative to the center of the sample, which allows us to implement sort of higher level filters directly in hardware. All right. So we've redone our high Z. High Z is kind of a cool block. If you think about fixed function, it generally starts with like reading geometry, and then you're translating the geometry, using matrix multiply in world space. So you're kind of moving these triangles around. But eventually you have to get to the point where you show a pixel. You're going to convert a triangle into a fragment, which you're eventually going to shade to draw a pixel. So that fragment processing is very important about order of those triangles on the final scene. So what high Z does is it remembers which triangle is closest. And if it ever sees a triangle that's further away, it'll instantly cull it from the pipeline, and we can dramatically improve performance. It's kind of a very smart trick to reduce pressure on your later shading. All right, so considering, again, the pixel backend, we have 2x blending throughput, which is, basically you've taken all these fragments, you've shaded them together, and when there's transparency, you have to blend them. So higher bandwidth for blending is critical. We've also got a 1.33 increase in our pixel color cache, which again reduces bandwidth requirements on our cache. All thrown together, it's a bubbly, delightful creature of comfort, okay? And we render target prefetch is increasing on the L2 cache. So we have a new 8 to N compression algorithm on our pixel backend, and we do fast clear. So a lot of you guys know that many times in a game, they'll say, forget what I drew in this last frame, and we're going to draw something new. And usually they use a clear command. And our older architecture would just write zeros. It's clear, so let's write zeros. Well, the truth is you can just mark a bit and forget about all the stuff that was there. So this is a brand new feature for our Xe2 architecture. It's like a kind of a no-brainer, but it dramatically improves performance. We have really dug in on ray tracing on Xe2. If you remember, this is a picture I used when I described our Xe2 ray tracing implementation. Ray tracing is kind of a fundamental algorithm in next generation games. The problem you're trying to solve is to figure out what triangle is a ray going to hit. And if you think about it, you could query all the triangles in a scene. You just basically sort them and then say, does this ray hit that triangle? It's a fairly simple math, but it's very slow. So what you do is you draw boxes, and then you nest boxes within boxes. That box hierarchy is called a BVH. And what you need to do is traverse that BVH to get to the lowest level box, and then you look at all the triangles that are contained within that lowest level box, and you only check those. So the thing that is searching through this tree is called a traversal pipeline. And in Xe2, we're now up to 3 traversal pipelines and 2 triangle intersection engines per ray tracing unit. So again, the triangle search happens at the leaf, and it's critical for ray tracing performance. You'll see that we now support 3 traversal pipelines, 18 box intersections, and 2 triangle intersections per ray tracing unit. All right, so back to the micros, right? We have done a ton of work. The work is spread all around the microarchitecture, and it impacts everywhere from geometry, sampler, backend, caching, and even the Xe core itself. And you can see that the performance varies somewhere between 1.2x for a tessellation test, all the way to some huge numbers that are checking out execute indirect. Okay, so that's a pretty good summary of where we are with the Xe2 architecture. It's brand new Xe core. It's our 2nd generation. We have new vector engines that are SIMD16. We've doubled down on ray tracing, 3 traversal pipelines and true triangle tests. We have deeper caches. We got a better performant XMX engine, and all about performance and efficiency. Okay, that is Xe2 in a nutshell. And the key thing to remember is this architecture is going to go multiple places. On the one hand, it's going to go down effectively into a Lunar Lake configuration. On the other hand, it's going to go up into a battle mage configuration. Okay, so both are supported natively by this architecture. That's why I don't call it Xe2 HPG. It's just Xe2, and it's going to cover the entire gamut of configurations. All right, so let's talk a little bit about Lunar Lake. So this is changing gears now. We're talking about a specific implementation. Lunar Lake is all about delivering experience. So on Lunar Lake, obviously, we have some key experiences. It's got to be low power. It's got to be high performance. It also has to be much more efficient because we're lowering our power budget. Remember, we talked about this. And it's got to support the latest industry standards. So for us, it's not just a graphics engine. It's got to have media. It's got to have display. It's a very complex device. By the way, I want you to start separating in your mind, separate media and display from Xe2. Xe2 is referring to our core architecture for graphics, and there'll be a media and display that kind of moves along on its own cadence. All right, so digging into Lunar Lake. On the graphics side, we know the big punchline, right? There are really three big blocks. There's the GPU, which we kind of talked about. It's Xe2. There is a fairly significant investment in media, and I'll go through the details of that for Lunar Lake. And we have a new display block, and I'll share you some of the new technology that shows up in display. Starting with the GPU, this is where we marry architecture and implementation. This is an 8 Xe core implementation, which is a fairly large investment. We have 8 Xe cores, 64 vector units, 2 geometry pipelines, and so forth. So think of it as a pretty beefy GPU for a very low power integrated device. If this is the curve that I think everybody's been waiting for, this is comparing Meteor Lake to Lunar Lake. And Meteor Lake came in 2 different variants. There's a Meteor Lake U and a Meteor Lake H. Our claim is that you will see up to 1.5x performance at the same power. Okay, so up to 1.5x perf at the same power. You'll also see significantly higher performance, I don't think I'm allowed to say, at the same or higher power. Okay, so if you imagine in the discrete world, this line would go further and the performance would go higher and the scaling would go wider. Okay, so natively around up to 1.5x performance. So let's talk about the implementation of the GPU AI engine. This morning, if you didn't come to my section, you didn't hear about our real plan and strategy for AI. It's a multi-engine strategy. We support AI acceleration on the GPU, on the NPU, and the CPU. So talking about the GPU specifically, it's all about this matrix engine. And we support 67 peak tops. Okay, the way to think about it is easiest with a demo. So are we ready on the demo? We are. Why don't we pull the demo to the screen? So Mr. Bart's a good friend of mine. Why don't you tell me what I'm looking at?
So here we have 2 platforms, and these are running on the platforms here on the stage in front of you here. So on the left-hand side, we have our Lunar Lake platform, and then on the right, we have Meteor Lake. Now, what we have set up here is Stable Diffusion running OpenVINO. And so what we're going to do here is we're going to generate an image, and we're going to use a prompt, and that prompt is older Intel engineer wearing a blue hat with a blue jacket. He is making a funny face with his mouth open, excited for new technology.
Yeah, but before you run it, let me tell you a little bit. If you haven't heard about Stable Diffusion, it is a transformer-based architecture. And so it's taking advantage of our XMX unit. It's running on XMX on Lunar Lake, and it's using DP4A GPU accelerated on Meteor Lake. So if you remember, DP4A is supported on our Xe architecture, and it's a 4-way int8 accumulation instruction, but it's not as optimized and performant as our systolic array is on Lunar Lake. So let's go ahead and give it a shot. All right, we're doing some compiling and text encoding. If you guys saw Darren's explanation, you realize there's a prompt that's being encoded by text. Then we're starting to do this UNet process, which is a diffusion. We're starting by injecting noise into the network, and then subsequent passes are basically evaporating the noise using a transformer. At the end of the day, we're done. So let's go back to the sheet before you show the punchline. So this took 6.3 seconds, which is pretty fast. Over on this side, we just finished, and it's 13.2 seconds. So we're demonstrating roughly a 2x performance of Lunar Lake versus Meteor Lake. And you can see this is the happy Intel engineer with the mustache. I don't get it. I don't have a mustache. That's a way older engineer than anybody I know. But at the end of the day, that is a great example. It doesn't look like me at all, really. I mean, but kind of, But anyway, that's Lunar Lake versus Meteor Lake, showing you the power of XMX and systolic versus DP4A. Thank you very much, Mr. Barnes. Let's go back to slides. Okay. So that was pretty cool, Stable Diffusion, and it runs obviously through our full software stack. Again, if you didn't see my morning session on the technology of a transformer, I actually think you should come to the afternoon session because it explains how Gen AI works, which is probably required reading for most of us. All right, back to the next block, display engine. So most of you know that display engine at Intel we've been working on it for a very long time. Can anybody guess why? Like, why is display so hard? Hey, come on, give me a guess. Anybody? Anybody? I'll tell you. Okay, hold on. Look at this picture. In the display engine, the top of it is reading the frame buffer. So if you think about what the top of the display engine does, it has to look at all the different formats, different resolutions, different formats. I'll talk about it in a little bit. Summarize at the top level first. So there's 3 display pipes, which are these pixel processing pipelines, which means you can have 3 different displays connected. We support 8K60 HDR or 3x4K 60 HDR, and even up to 360 hertz 1080p and 25x14. So the key thing is, there's actually a brand new interface on the Lunar Lake display engine, which is called EDP 1.5, and I'll talk all about that in just a second. So it's a very high-performant display interface. The way to think about it, well, the way to think about it is, did I skip a slide? Let me go back a little bit. I really wanted to do that other one. I guess I didn't keep it. All right, so we're going to talk about at the top of the engine. Remember, the input to this block is the read of a frame buffer. And frame buffers have multiple different formats. They have multiple different gamuts. They have different resolutions. So the process of streaming that in, it also does decryption for encrypted video. But at the end of that, it comes into our pixel processing pipeline. Okay? So the top part of the pixel processing pipeline is processing 6 planes of frame buffers. So you can have overlays, you can have different compositions, but they can all be different formats and they can all be different resolutions. So that front part of the pixel processing pipeline, it does things like color conversion, scaling, and composition, all in hardware. It's actually super crazy. I spent like a week trying to understand what this thing does, and it is super elegant. But once you get to this part, think of it as you have a common format and a common gamut for all the planes that have been composited. The next step is to target it towards a specific display. So once you have a common format, you're going to, again, do color enhancement, you're going to do scaling to match your display, and you're actually going to do conversion for protocol based on whether it's HDMI or EDP or whatever, right? So this back half, think of it as generating pixels. Pixels that are going to transport over whatever connection you have. Pretty cool, right? The front half is frame buffer, the back half is display pixels. All right, so there's one special pipe. This pipe is kind of targeted at laptops. So most of the time, Lunar Lake is going to be, actually all the time, Lunar Lake is going to be in a laptop. And there are things that you can do in a laptop to optimize the experience far beyond a normal desktop chip. So let me talk about a few things. There's one which is called panel replay, and the second thing is called brightness sensing and lace. And so on that specific pipe, we have additional power management to implement these 2 features. I'm going to go really quickly through how these work. So well, before I do that, the pixel pipeline at the end of the day has to go through compression, and then there's transport and encoding. So if you think about it, we've kind of generated pixels. Now we're going to encode it, and then we're going to shift it to a specific physical interface. We have 3 different physical interfaces. Actually 4. It can be DP HDMI, DP HDMI, DP HDMI, or EDP. And so what this block's responsible for is effectively converting the generic pixel format to a specific targeted interface. Lastly, we've got this display stream router, which implements a technology called MST. If you're familiar with DP, you can actually chain heads there. That's all happening in this stream router. And you can also steer any head to any connection. So basically, plug and play is implemented in the router. So let's talk about the new thing, EDP 1.5. So EDP 1.5 is all about panel replay to lower power. And it is an evolution of panel self-refresh with selective update and adaptive sync controlling the source. So this is a technology that's near and dear to my heart. It basically says that the GPU can control when the panel refreshes. And it's a pretty fundamental innovation that allows us to solve some really cool problems. The first one is media playback. So if you imagine trying to play a movie on a laptop, the movies are generally captured in 24 frames per second. So a 24 frames per second movie really doesn't work on a 60 hertz panel, right? You're going to have to show 2 times of 1 frame, and then three times of the next frame, and then 2 times, and then 3 times. It's called 3-2 judder. And the reason it's called judder is because the animation captured in each frame is the same. So if you show B 3 times and you show A 2 times, you're going to feel a little hitch every time you switch between that pattern of 3 and the pattern of 2. The way adaptive refresh fixes this is it allows us to set the panel refresh to 48 hertz when we're playing back a movie. So at 48 hertz, you'll see it's just 2 frames and then 2 frames and 2 frames and 2 frames because the content is captured at 24 hertz. Okay, so that's how adaptive refresh actually gets rid of judder in movie playback. The next tech I want to talk about is panel kind of refreshing. So I'm going to roll through this pretty quickly, but back in the day, you basically had the display engine turn on, you rendered an image, you accessed memory, and you shifted it to the display. All of this consumed a lot of power, and you did it on every frame. The first innovation was, hey, why don't we kind of speed the data to the display? So we'll actually run the interconnect faster than the refresh, so we can shut down the memory interface sooner. The next innovation was panel side refresh, self-refresh. So what we're doing here is we're capturing the data, we're sending it over to the panel, and then we ask them to implement a buffer inside the panel to record that image so that if the next frame doesn't change, then on the next refresh, we'll just refresh the panel itself without retransmitting the data. The next interface change after that was something called selective update. In this technology, we said, hey, when you're playing a movie, there's often these bands here, right at the top and the bottom, so let's not send those. And as a matter of fact, this selective refresh can be a box that's as arbitrary size. So again, that allows us to shut down the display box sooner and save power. Next innovation, selective update with hardware queuing. How about, instead of waiting to send the new frame, because I'm decoding media in this case, I'll actually send a bunch of frames at the same time. I'll turn on and I'll burst the frames, and so when I get to this next frame, it'll just already have the data and we don't have to wake up. What's new with EDP 1.5 is something called early transport. With early transport, we actually send the data very, very quickly. It's actually going to transmit all the data to the display engine, and it never, ever actually turns on the core again. So it's another improvement upon what we're doing. It actually is a standard in EDP 1.5, so it should be broadly disseminated. Summarizing it all up, you know, it's kind of like all about power savings. So the technologies I just described to you save collectively about 112 milliwatts when you're doing windowed YouTube. It saves about 13 watts when you're doing, 13 milliwatts when you're doing full screen, and 65 milliwatts when you're doing, what's that saying? Oh, fork tab browsing, so browsing, right? But that's not the only story. We've done a lot more on display. This actually summarizes all of the improvements that we've made inside the display block for Xe2. And you can see things like, you know, early display engine waking, saving 351 milliwatts for full screen YouTube. This is all of the impact of the Lunar Lake display engine on power for common use cases. All right, the last block, the media engine. Okay, so the media engine has actually been significantly improved. We now have an 8 megabyte side cache, which is shared, but allows us to save some intermediate data, and it improves performance and power for media decode. The block itself is a single MFX engine. It's organized into an encoder and a decoder, which I'll talk about in some detail, and a bunch of fixed function logic for, again, gamut scaling and video scaling, depending on your target. We support 8K60 10-bit HDR decode and 8K6 10-bit HDR encode. So both encode and decode is supported, and all of the major codecs, including a brand new one called VVC. So VVC is the next step in video encoding, and we're pretty excited to support it natively on Lunar Lake. So VVC significantly reduces the bit rate at the same quality level, and it has 4 main features. One is a file reduction size, so the files are getting more compressed and better compression ratios. It supports adaptive resolution streaming. That's a pretty cool technology I'll talk about. We support screen content coding and 360-degree projections primarily for cell phones. So let's dive into these techs one at a time. First of all, this is like a major problem that happens all the time. When you're streaming YouTube, like you're watching, a YouTuber's channel, it starts off at high res, maybe 4K, but then there's some kind of buffer interference. So what happens is the client tells the server, hey, I'm not getting all your frames. And then the server responds by effectively flushing the cache. Right? You throw away all the frames that are in place, you throw out all the keyframes and the iframes, and you start over. So right here, there's a hitch. We've all experienced it watching YouTube, right? The thing bandwidth, and it's like stirs a little bit, and then it goes to a lower resolution. And the opposite happens when you get more bandwidth and you go to a higher resolution. So what's happened with VVC is effectively we can preserve the data that we've sent. So you might be having 4K frames, and then the interruption happens, and the client tells the server, hey, some stuff's happening. So instead of tearing down the stream, the information starts being incremental at a lower resolution. So keep the data that you've got, but now the new frames are going to be lower res, and we just have the logic to put that back together. And conversely, when we get better bandwidth, we'll reuse the reference frame data from the prior frames. So it's pretty cool, and that's a feature of VVC. Now this picture I have here because it's the way our encoder works and our decoder works in detail. This is the decoder process. I did a video on this. It's a little bit too technical to go in here right now, but let's just say that for our new generation of media encoder and decoder, we've messed with pretty much everything. So everything's been widened up, or our search depths have been improved, and of course we now support VVC. This is a kind of a block diagram of it where you do the decoder and encoder, video scaler, and all this color space conversion that lets you kind of take a video, decompress it, and send it to any display. This is a super cool technology called screen content coding. And the idea is that normal media codecs were designed for movies. Right? They were designed for movies because that's really what we stream. They're not designed for desktop streaming or sharing a workspace from the cloud. So you'll see here on the left side is including screen space coding. And I guess that's right side. Right side is screen space coding, and left side is without. And hopefully you can see the algorithm that we use is pretty different. And the quality is much, much better at the same bit rate. So screen space coding or screen content coding dramatically improves the experience for streaming of a desktop, whether you're streaming from the cloud or to a neighboring desktop. So let's talk a little bit about the evolution of codecs. This is a very hard problem because codecs have been changing for 20 years. It started really with MPEG-2, and the process has increased complexity. So these codecs are now very complex, but the truth is we've implemented all of it in hardware. So with the latest incantation of H.266, we're now about 100x the complexity that we were when we started off with MPEG-2. But that 100x is totally invisible to users because it's all implemented in hardware. All right, so with that, I want to show you what this looks like. So let's go ahead and pull up the demo. All right, cool. So what are we looking at here?
So we're looking at 4K VVC playback on both Lunar Lake and Meteor Lake. However, with Lunar Lake, we have hardware accelerated decoding. And you can see there's a big power difference there.
Big power difference. So on your right side here is hardware accelerated VVC decode. It's a 4K display. On your left is actually a Meteor Lake running without hardware decode. So you can see hardware decode actually makes a huge difference. By the way, the video that you're looking at is the installation of an ASML device in our Hillsboro facility for the latest gen lithography. So we're also very excited about what's happening on the foundry side. But this is not about that. This is all about dramatic power reduction by implementing VVC inside of our codec. By the way, do you see the blue lasers? That's pretty cool. It's evidently evaporating aluminum. Who knew? Tin. Who said tin? Is it tin? I thought it was aluminum. It's tin?
It's droplets of tin.
Have you been there? Has anybody in this room been to see this? No? Stephen, you didn't go?
I went, but not for this.
Oh, okay. Well, it's very, very cool. I actually am so excited to see this kind of stuff, and hopefully we'll have more to share there. All right, coming back. Back to slides, please. So obviously, it's not just about the hardware, although we do have some kick-ass hardware. You have to have a complete software stack. So in this case, we've been working on it, right? And it's complicated. On this side, we're talking about media with FFmpeg and GStreamer, VPL and D3D. That's like a media interface. HMFT and VPL are also Microsoft standard for media. Then you get into the VPL, which is an Intel standard for media. So this half is like a software cornucopia for doing media encode and decode. On the left side, you'll see D3D and Vulkan, which we have spent an amazing amount of time with. And it's all been mostly down here in our graphics UMD driver and inside of our KMD driver. We've been improving them for years, and I'm really proud to say we've made dramatic improvements. But for us now, it's not just about this software stack. There's a little bit more, and it's kind of on the side. So our first incantation of this layer is called XeSS. And XeSS, it kind of sits above the driver, and it's an effect that uses our XMX block coupled with deep learning to do super sampling, okay? So you can render at a lower resolution and then sample up, and this is obviously a key part and supported on Xe2, okay? So with all that, I think we need to see a demo. So let's go ahead and pull up the demo, okay? Now, what are we looking at here, Mr. Bartz?
We're looking at F124 from our friends at EA and Codemasters. It is just launching today. And as you can see, we're playing at 1080p with high settings with ray trace shadows enabled and XeSS performance mode enabled.
That's very cool. So I want to draw attention to a few things. First of all, this is a brand new game. And it's actually one of the first times that Intel has been able to show a brand new game on the day of launch on our graphics card. That is tremendous performance and tremendous progress. It's above 60 frames per second. It's using XeSS. It's giving you a smooth and seamless experience. And I'm not going to talk too much about the power, but let's just say it's definitely working within the Lunar Lake power budget. So with all that said, I think that's a good snapshot. Let's go ahead and pull it back to slides. Lunar Lake GPU is accelerated by Xe2. It is approximately, up to 1.5x faster and the same power budget as Xe. It offers 67 TOPS. It has 8 ray tracing units, each of which have 3 traversal units and 2 triangle intersection units. We support hardware decode for VVC, AV1 encode and decode, and up to 3 times 4K 60 display interfaces. We are very efficient in our Xe core. It's our 2nd generation Xe core. And lastly, we support EDP with 8 Xe cores. So that is Lunar Lake, people. I'm so excited. It's been a tremendous step forward, and I can hardly wait till you guys get it in your hands to test. But Xe2, it's definitely coming. All right, that's it. Let's say thank you. And any questions?